Uniform circular motion with forces. Let's do some evens. Suppose the coefficient of static friction between the road and the tires on a car is 0.6. Pretty low for that. And the car has no negative lift. So that just means there's no other forces that you have to worry about in doing this. What speed will put the car on the verge of sliding as it rounds a level curve of radius 30.5 meters. All right, so the force diagram for the car would look like this. If it's a level road, which a lot of turns are not, I wonder if you've ever noticed that. I mean, of course, this is true on racetracks when cars are going very fast. That situation, the turns are banked. But even if you go, like for example, if you're leaving the high school and you go up to that light and you're getting on that big ramp, if you're getting onto 81 North, if you pay close attention to what's going on there, that road is banked. And what's the point of doing that? If the road is banked, it tips the normal force toward the center of the circle, and that means you can go faster without skidding off the road. Not suggesting that you should try to push the limits there. All right, so anyway, what about this? So here our unbalanced force toward the center of the circle is going to be equal to the friction force, and we're going to try to max that out. So unbalanced force toward the center of the circle has got to be mv squared over r. Our maximum friction is going to be mu times the normal force. Well, that's mu mg, and those masses cancel out. Good thing, because I didn't know the mass of the car. And they want to know what is the max speed. So that's going to be the square root of mu g r. So that's 0.6 times 9.8 times 30.5. About 13.4 meters per second. That's only about, I don't know, 30 miles an hour-ish. So that is a tight turn. Be careful. Watch out. Let's see, 42, they converted their answer, well, that's fine. They converted to kilometers per hour, but that's good. You're not looking at the back of the book for these anyway, because they're evens. 44, during an Olympic bobsled run, the Jamaican team makes a turn of radius 7.6, at a speed of 96.6 kilometers per hour. If you're wondering, like, why is this book so obsessed with kilometers per hour? What's up with that? Well, when you're talking about that kind of speed, like the speeds of cars and other such things, like bobsleds that go about that range of speed, the rest of the world uses kilometers per hour. So it's a nod to that, I think. Of course, we need it in meters per second. So there's that. And what is their acceleration in terms of g? So the acceleration toward the center of the circle is equal to v squared over r. So we don't actually need to use any considerations about forces here, because they're just asking about the acceleration. So v squared over r here is going to be 96.6 squared over 26.8. Of course, that acceleration is toward the center of the circle. (348 meters per second squared). Oh, I used the, wait a minute. What did I do here? Oh, these are the wrong numbers. This is totally wrong. Sorry. I just grabbed some numbers there. Got to be more careful than that, people. I did that on purpose, just to show you an example of somebody being reckless and just grabbing numbers and throwing them down into some equation. So I hope you learned a lot from that. It's a good teaching moment there. 26.8 squared over 7.6. There we go. So that's 94.5 meters per second squared. And then they want it, like how many G's is that? Well, 1 G is 9.8, so dividing that by 9.8, I get about 9.6 G. Now, what does that mean in terms of forces and how these bobsled riders are going to feel? Well, if you feel 1 G, that's like regular, like just standing there, sitting there, moving at a constant velocity or at rest. That's when you feel 1 G. So 9.6, that's 9.6 times what you usually feel. So you're going to feel pretty heavy doing that. 46. Got a police officer in hot pursuit drives her car through a circular turn of radius 300 meters with a constant speed of 80 kilometers per hour. Her mass is 55 kilograms. What are the magnitude and angle relative to vertical of the net force of the car's officer in the seat? And then, so we need to consider both horizontal and vertical. So here's our officer. Say that center is over here. Turn. So there's going to be some forces now if you're like, oh, that's the tires on the road. Well, no, it's not the tires on the road, because this is a free body diagram or a force diagram of the forces on the officer, the actual passenger in the car, or driver of the car, rather. So what's providing that force? Well, there's forces from the seat, and I guess if you turn hard enough to the right and you're the driver, this door could end up pushing on you if you're like really pinned up against that door, providing some of that force. Probably it's just mostly forces from the seat. So what they're asking is what is the total amount of force, magnitude and angle, of the net force from the seat. So those are the forces that are coming from the seat. This all has to come from the seat. This all support has to come from the seat. So we need to find those and add them up vector style. All right. I was looking at if it said if she's turning right or left, but it doesn't matter because when I add these two together, the angle relative to vertical, that's this angle right here relative to vertical that they're looking for. It would be the same regardless of which side we put it on. Okay, so let's see. This is going to be equal to mv squared over r, and that is mv squared over r and this is force, sorry, it's newtons. So 89 newtons toward the center, and then here, if her mass is 55 kilograms, then that normal force is going to be equal to about 540 newtons. So I've got a horizontal component. Why did I draw it that way? That was weird. Sticking with my scheme here, I've got these components, and I'm actually looking for this angle because they said, what's the angle from vertical? But maybe I'll just do, so I'm going to Pythagorize these anyway. This is my 89, this is my 540 newtons. I think I'll just find this angle, tangent inverse rise over run, because I'm used to that, and then I can find the complement of that. So, let's see, square root of 89 squared plus 540 squared. It's about 547. And this angle, tangent inverse rise over run, is about 80.6 degrees. And then, of course, if you did tangent inverse run over rise, you could just do that too. Or 90 minus that gives you the same thing. So that's about 9.4 degrees. So 547 newtons, 547, there we go, newtons at 9.4 degrees from the vertical. Let's confirm that here. Yep, I rounded a little differently. That's good. 48. Roller coaster car has a mass of 1,200 kilograms when it's all loaded with people and their cell phones and stuff. As the car passes over the top of a circular hill of radius 18, never pass up an opportunity to draw a roller coaster. Ooh, that's the person's arms up in the air. That looks weird. Probably not going that fast, actually. Right at the top of the hill, probably not going that fast. Let's see. As the car passes over the top of a circular hill of radius 18 meters, its speed is not changing. At the top of the hill, what are the magnitude of the normal force and up or down of the normal force on the car from the track if the car's speed is 12 meters per second? I get that 12. It says 11. Right. All right, so force diagram here. If you're going over the top of a hill, there must be unbalanced force toward the center of the circle. So there's force of gravity, but the normal force is going to have to back off so that there can be unbalanced force toward the center of the circle. Gravity's got to be winning because that's the direction toward the center. So the normal force is going to be mg minus mv squared over r. So that's 1,200 times 9.8 minus mv squared over r. Let's pop that out of the calculator. And that's about, with two sig figs, it's 3,700 newtons is that normal force. And they want to know what is the direction also up or down of the normal force on the car from the track. So on the car from the track is up. So this is A, B is up. How about the normal force on the track from the car? Well, that's a Newton's third law pair, equal opposite. So that would be the exact same amount but down, right? If the track is pushing up on the car, then the car is pushing down on the track, because there's only one car-track interaction. It cannot be different amount. It's impossible. Okay, so now we want the normal force in direction if we change to 14 meters per second. So I've got that all set up here. You can just crank that out. And what? Let's go. Let's pull it here. And this, I'm getting a negative number here doing this. So what does that mean? Well, that means this must be the kind of roller coaster where like the wheels are kind of attached to the track, because this is too fast. 14 meters per second is too fast to go over that hill without it flying off, unless the wheels are kind of attached, and there's plenty of roller coasters where that is the case. So what does that minus sign mean? It means my assumption that the normal force was up was incorrect. So this means that the normal force is actually down, that the track has to be pulling down on the car to hold it in that turn. All right. One more. Let's see if I can fit it up here. Number 50. An 85-kilogram passenger is made to move along a circular path of radius r equals 3.5 meters in uniform circular motion. Figure 640A, okay, got some graphs here, is a plot of the required magnitude of the net centripetal force for a range of possible values of this passenger speed v. What is the plot's slope at v is equal to 8.3? All right, so I've got a graph. I'm just going to make a sketch of these. They're kind of just pretty sketchy graphs anyway, aren't they? I got force versus velocity and force versus period. And this one looks like this, which makes sense because if you think of this, force equals mv squared over r. The m and the r are constants, so that should look like a upward opening parabola. And then here, this looks like some kind of inverse relationship, doesn't it? All right, so we have here this information. Let's get the right units there. And plot required, what is the plot's slope for the force versus v? So that's a derivative, right? So let's see. We know that this is true, right? So what's the slope of this? Well, so df dv is equal to m over r to v, and that would be it. So when v is equal to 8.3, what's the slope? Well, it's 2 times, if you're thinking, oh, is this like related rates? No, it's not, because I just took the derivative with respect to v. Like I just pretended, you know, as if this was y equals some function of x. So we're just taking the derivative times v. It feels a little bit like related rates, though, I think. Times 8.3. So let's see how we did there. So that's about 403. And what would the units of the slope of this be? Newtons over meters per second. All right, that's part A, I believe. And for part B, they want to know what's the slope of this. So if I'm going to do that, I need an equation that relates these things. So let's think about that for a minute. So I've got force is equal to, I know that the sum of all forces is equal to mv squared over r. Now I'd like to have this as some kind of function of t, so let's see if we can do that. The m and the r are constant, and the v is equal to 2 pi r over t. So I think I need to substitute this in here if I want to be able to do this, if I want to look at this relationship between force and time period. So let's see, I've got the m and the r. Probably I need to do a couple of steps here, and then this whole thing squared. So that squared is 4, that squared is pi squared, that squared is r squared, and that's period squared. So I thought maybe this looked like, looks like an inverse. It's actually inverse square, like a y equals 1 over x squared kind of situation. One of the r's cancels out, and I get here, I'm going to put the constant all out front. So I have 4 pi squared m r, one r left there, times period to the negative 2. So the derivative, in other words, slope of this graph, is equal to, multiply the negative 2 here, that's negative 8 pi squared mr, that's all just a constant, times t to the negative 3. Right. And now, let's see if we can get an answer. So they would like us to figure the period out when this is 2.5. So I'm just going to jam this all in my calculator. Negative 8 pi squared times the mass, which is 85, times the radius, which is 3.5, times the period, which is 2.5, to the negative 3. And let's see how we did there. Good. So that's about negative 1,500. What would the units be of the slope of this? Well, this is newtons and this is seconds. Rise over run. That's it.